Hello everyone. So till now we have considered forced convection. In forced convection, the fluid is forced to flow over a surface or inside a tube by external means like using pump or blower. Today we will start natural convection, which is also known as free convection. In natural convection, fluid motion starts in natural way due to the temperature difference, and hence there will be density difference and in the presence of acceleration like gravitational acceleration. So, you can see natural or free convection flow arises when a heated or cold object is placed in a quiescent fluid, the density of which varies with temperature. So, these are some typical applications: heat transfer from pipe, dissipation of heat from a coil of a refrigeration unit to the surrounding air, heat transfer from a heater to room air, and atmospheric circulation. So, as I told before, that two conditions are required for fluids to set in motion in natural convection: the presence of an acceleration field like gravity and a density gradient in the fluid, which may occur due to temperature gradient. So, you can see here in the right hand side figure. So, if you keep one hot egg in a plate, then obviously surrounding fluid's temperature is lower than the hot egg. So, the fluid which is coming into contact with hot egg will have higher temperature and it will have lower density and it will go up. Okay. So, warm air will go up and cool air will come to the hot egg, again it will get heated and it will go up. So, in this way you can see that fluid motion starts. Another example of this cold soda. So, it is actually warmed up in presence of the ambient air. So, you can see when you keep it in the ambient air, warm air will come into contact, there will be heat transfer, its density will increase and it will go down. So, obviously warm air will come into contact in the upper half and there will be heat transfer, due to that its density will increase and cool air will come down. So, these are some examples of natural convection. We can have simplest natural convection solution for flow over vertical plate. So, if you consider this vertical plate which is maintained at temperature Tw, okay, and the quiescent fluid is having temperature T infinity and its density is rho infinity. There will be acceleration field and that is your gravity. So, we are taking x as normal to this vertical plate and velocity in that direction we will consider as u, and along the plate we are taking y coordinate and velocity in that direction will be v. As Tw is greater than T infinity, obviously your fluid will go up and thermal boundary layer and hydrodynamic boundary layer will form over this plate. So, here you can see in the first figure. So, there will be hydrodynamic boundary layer formation whose hydrodynamic boundary layer thickness is delta, and you can see the velocity distribution. Obviously, for no slip condition on the vertical wall velocity will be 0 and outside ambient is quiescent fluid. So, obviously at the edge of the boundary layer velocity will be almost 0. So, maximum velocity will occur inside this hydrodynamic boundary layer. If you consider the thermal boundary layer, so similarly it will also start from the bottom and delta T is the thermal boundary layer thickness. It will grow as you go up, that means with increase in y delta T also will increase and T infinity is lower than Tw. So, this will be the temperature distribution. So, at the wall you have Tw, and at the edge of the thermal boundary layer you have temperature T infinity. If you consider Tw less than T infinity, so in that case your boundary layer will start forming from the top edge. So, that will be your delta, and also you have thermal boundary layer delta T. So, this is your delta T and this is your delta, and this is your direction y, okay, and this is your x. This is your Tw, and quiescent medium is having temperature T infinity. So, first we will write down the governing equations for flow over vertical plate. Let us first make the assumptions. So, you can see the flow is steady, laminar and 2 dimensional, viscous dissipation term is neglected, and obviously we will have boundary layer approximation is valid. Okay. And if we consider the height of the vertical plate as h, then we can consider that delta T by h will be much less than 1. Okay. Temperature difference between the plate and the fluid is small, in which case the fluid may be treated as having constant properties. So, we are considering the temperature difference as low, and the thermophysical properties like viscosity, thermal conductivity, specific heat, will assume that these to be constant. Also, with one exception, the fluid is incompressible. The exception invokes accounting the effect for the effect of variable density in the buoyancy force, since it is this variation that induces fluid motion. So, you can see another important assumptions we are taking, that we are considering rho to be constant, so that it will become incompressible, but as temperature difference will be there, there will be density difference, and that density difference effect will take into account in buoyancy term only, and rest other terms like continuity equation and the inertia term of the momentum equation will take rho as constant. So, in natural convection, whatever we discussed just now, that is known as Boussinesq approximation. Okay. The basic approach in this approximation is to treat the density as constant in the continuity equation and the inertia terms of the momentum equation, but allow it to change with temperature in the gravity term. Okay. So, this is important assumptions we are taking, which is known as Boussinesq approximation. So, in this approximation what we are telling, that we will take density as constant in the continuity equation as well as in inertia terms of momentum equation, but we will take the effect of its change in the buoyancy term. So, first let us write the governing equations. So, what are the governing equations? First is continuity equation. So, we consider 2 dimensional flow. So, it will be del u by del x plus del b by del y is equal to 0, and x momentum equation. Okay. So, rho u del u by del x plus v del u by del y is equal to minus del p by del x plus mu del 2 u by del x square plus del 2 u by del y square, and y momentum equation. Rho u del v by del x plus v del v by del y is equal to minus del p by del y plus mu del 2 v by del x square plus del 2 v by del y square. Now, we will take the body force term. So, what is the body force term in the y momentum equation? Okay, z is acting in the negative y direction. So, it will be minus rho g. Now, first write down the boundary layer equations. Okay. So, as we discussed in the forced convection in boundary layer approximation, that delta T is much less than H. Okay. So, in this particular case you can see that delta is the hydrodynamic boundary layer thickness and delta T is your thermal boundary layer thickness, and that will be much smaller than the height of the plate. So, in this case now you can have the assumptions. So, if you have the similar way as we have done in the forced convection, you can neglect del 2 V by del y square, and here in x momentum equation all these terms will become negligible only from here. So, all these terms will become negligible and you will have del p by del x as 0. Okay. And as del p by del x is 0, p is function of y only, then y momentum equation you can write as rho u del v by del x plus v del v by del y. Okay. So, this you can write now is equal to minus dp by dy plus mu del 2 v by del x square minus rho g. Okay. So, this is your boundary layer equation for flow over vertical plate, and this is your y momentum equation. In x momentum equation you will get del p by del x 0. Now, let us write the energy equation. So, in general your energy equation is u del t by del x plus v del t by del y into rho Cp is equal to k del 2 t by del x square plus del 2 t by del y square. Okay. So, if you write the boundary layer equation, then it will be 0. So, this is your energy equation. So, you can write u del t by del x plus v del t by del y is equal to alpha thermal diffusivity k by rho Cp del 2 t by del x square. Okay. Now, you see the y momentum equation. In the y momentum equation, in the left hand side we have density rho. Okay. So, invoking the Boussinesq approximation, we will take rho as constant and it will be same as rho infinity. Okay. So, in the free stream pressure whatever you have rho infinity which is actually quiescent medium. So, that will be rho is equal to rho infinity. So, invoking the Boussinesq approximation, we will take the rho in the left hand side of the y momentum equation as rho infinity, which is your quiescent medium density rho infinity. So, you can see this rho infinity. So, we can write down all these boundary layer equations now. So, we can write these boundary layer equations. So, what we invoked, we have taken x as order of delta t, okay, y as order of h, and we have assumed delta t is much less than h, okay, and we have dropped del 2 by del y square these terms. So, your continuity equation will remain same, del u by del x plus del v by del y is equal to 0, and invoking the Boussinesq approximation and rearranging, you can write the y momentum equation as u del v by del x plus v del v by del y, okay, is equal to minus 1 by rho infinity dp by dy plus nu del 2 v by del x square Now you have bouncy term. So, what is your bouncy term? So, bouncy term will become minus rho by rho infinity into g. Okay. So, now here you can see how we will calculate the dp by dy. So, dp by dy you can write as dp by dy as dp by del p by del x is 0. So, dp by dy you can write dp infinity by dy, because del p by del x is 0. So, whatever pressure is there outside the boundary layer, so that will be impressed inside the boundary layer. So, now in the quiescent medium, so you can write the hydrostatic pressure, right. So, what will be the dp infinity by dy? So, this you can write as minus rho infinity g. Okay. So, this is your from hydrostatic pressure distribution you can write it. So, obviously you can see now these two terms together you can write this term and this term you can write as minus 1 by rho infinity dp by dy minus rho by rho infinity into g. So, this you can write. So, it will be minus rho infinity g. So, it will be rho infinity by rho infinity into g minus rho by rho infinity into g. So, it will become rho infinity minus rho divided by rho infinity into g. So, your momentum equation bouncy term you can write as rho infinity minus rho divided by rho infinity into g. And now you can expand the rho in Taylor series, expanding rho in Taylor series. So, what you can write? Rho is equal to rho infinity plus t minus t infinity into del rho by del t plus higher order term. Okay. So, neglect this higher order term, and you also you can have volumetric expansion coefficient as volumetric expansion coefficient. You can write beta is equal to 1 by volume del V by del T. So, here this is the V volume at constant pressure. So, in terms of density if you write, so it will be rho del of del T 1 by rho at constant pressure. So, it will be minus 1 by rho del rho by del T at constant pressure. So, what you can write? Del P by del T is equal to minus beta into rho. So, similarly you can write del, sorry, this is your rho. Similarly you can write del rho by del T at infinity as minus beta rho infinity. So, if you invoke this in this equation, so what you will get? You will get rho is equal to rho infinity plus t minus t infinity into minus beta into rho infinity. So, you can rearrange and you can write rho infinity minus rho as rho infinity into beta into t minus t infinity, and rho infinity minus rho into g you can write as rho infinity beta into g t minus t infinity. So, now you can see this term rho infinity minus rho into g, now you can substitute that term. So, and rho infinity minus rho divided by rho infinity. So, you can write rho infinity minus rho into g by rho infinity as beta into g t minus t infinity. So, this is your bouncy term. So, now your boundary layer equations will become continuity del u by del x plus del V by del y is equal to 0. Your x momentum equation will become u del V by del x plus V del V by del y is equal to, now you have nu del 2 V by del x square. Now the buoyancy term beta into g t minus t infinity, okay. And you have energy equation u del t by del x plus b del t by del y is equal to alpha del 2 t by del x square. So, these are the boundary layer equations for flow over vertical plate, okay, for the case of natural convection, and we have assumed density to be constant in continuity equation and in the inertia terms of y momentum equation, and we have taken the change of density only in the buoyancy term, okay. So, these are the equations. Now, we will do the scale analysis and we will try to find what is the order of heat transfer coefficient and the Nusselt number, and which are the forces is dominating for high Prandtl number fluids and low Prandtl number fluids for constant surface temperature. So, first we will consider uniform surface temperature case, then we will find the order of magnitude of this heat transfer coefficient and the Nusselt number. So, inside the thermal boundary layer, your x will be order of delta t, y will be order of capital H, where H is the height of the plate, and we are assuming that uniform surface temperature. Okay. And the continuity equation, if you see, that will be del u by del x plus del b by del y is equal to 0. So, if you see the order of magnitude of u, so u by delta t will be order of v by h. Okay. So, from here you can see u will be order of v into delta t by h. From energy equation now, so this is your continuity equation. Now, from energy equation, u del t by del x plus v del t by del y is equal to alpha del 2 t by del x square. Okay. So, the order of delta t will be T w minus T infinity, and this delta t will be order of delta t. So, you can see here you can write u delta t by delta t. So, this is the first inertia term. The second inertia term, so you can write v delta t by h, okay, and the diffusion term will be alpha delta t by delta t square. Okay. So, now you can see if you put u is order of v delta t by h. So, if you put it here, you can see it will be equivalent to v delta t by h. So, you can see these inertia terms are comparable because these are same v delta t by h, and this is your diffusion term. So, now inertia should be comparable with the diffusion term. Okay. So, if you do that, so you will get v delta t by h will be order of alpha delta t by delta t square. So, from here you can see the what is the scale of v. So, v scale will be alpha into h by delta t square. So, we have found the scale for v, and similarly from this equation you can find the scale for u. So, u will be alpha h by delta t square delta t by h. So, u scale will be alpha by delta t. Okay. So, now from using continuity equation and the energy equation we have found the scale for velocity u and v. Now, let us consider momentum equation. So, momentum equation we have u del v by del x plus v del v by del y is equal to nu del 2 v by del x square plus the Buoyancy term. So, these are inertia terms. Okay. This is your viscous term and this is your Buoyancy term. Okay. And what is the order we have? X we have delta t, y we have h, u we have alpha by delta t and v we have alpha h by delta t square. Okay. So, using this scale now let us see each term. So, the first inertia term if you see, so if you put u alpha by delta t, okay, v alpha h by delta t square, okay, and x is delta t. So, this is your first inertia term. Second inertia term now v, so it will be alpha into h by delta t square, again v, so this will be square and y is your h, so 1 by h. So, first look at these two terms. So, if you see, so it will be similar as alpha h by delta t square whole square 1 by h. Okay. So, this is equivalent to this. So, you can see these two inertia terms are of same order because both are having the same order alpha h by delta t whole square 1 by h. Now, let us see the viscous term. So, in the viscous term now we have nu. So, v order is alpha h by delta t square and x order is 1 by delta t, and this Buoyancy term. So, g order of g beta and delta t. Okay. So, now what we will do? We will just divide these terms with g beta delta t. So, that it will become 1 Buoyancy. So, we are dividing, okay, by g beta delta t. So, you will get, so this term if you see, so it will be nu into alpha into h, okay, by delta t cube, then g beta delta t. So, this is your viscous term and now you divide this term. So, these two terms are same. So, I will write only one term. So, it will be alpha square h square by delta t to the power 4 h, and we are dividing by g beta delta t. Okay. Now, we will rearrange it. So, if you rearrange it, so you can see the viscous term. Okay. We will write it as, so this will be 1 Buoyancy term, it will be g beta delta t, we will write h cube, then we have alpha nu. So, now h cube we have just divided. So, we will multiply in the numerator h. So, it will be h cube, sorry, here this term 1 by delta t. So, it is x square, right. So, it will be delta t square. Okay. So, you see it is x square. So, x is order of delta t. So, it will be delta t square and it will be delta to the power 4. Okay. So, now this will be h cube into h 4. So, h by delta t to the power 4. Okay. And this term we will write it as, first we will write h by delta t to the power 4. Okay. So, h to the power 4 we have written. So, in the numerator there will be h cube and this we can write as g beta delta t h cube. Okay. And we have alpha square. So, we will write alpha into nu and we have multiplied in the numerator nu. So, we will divide this in the denominator. So, it will be alpha by nu, because alpha square is there. So, it will be alpha by nu. So, you can see, you can write it as, now Prandtl number, you know, right, what is the Prandtl number? So, Prandtl number you can write nu by alpha, and we will define another non-dimensional number, that is known as Rayleigh number. So, Rayleigh number we are defining as g beta delta t h cube by alpha nu. So, what you can do now, this you can write as h by delta t to the power 4. So, this is your Rayleigh number to the power minus 1, you can write this as Prandtl number to the power minus 1. This is your h by delta t to the power 4. Okay. And this will be your Rayleigh number to the power minus 1, and Rayleigh number we have defined based on the height of the plate. So, this is, you can write h, here also you can write h, and this is the buoyancy term, this is 1. Now, we will consider two different cases, one is high Prandtl number fluids and low Prandtl number fluids. So, for high Prandtl number fluids, Prandtl number will be much greater than 1, and you can see in this particular case. So, it is 1 by Prandtl number. So, if it is 1 by Prandtl number and Prandtl number is very high, so this term will be dominant term. Okay. So, this term will be dominant term for the high Prandtl number fluids, and when you have low Prandtl number fluids, so obviously this will be your dominant term, but in each cases buoyancy term should be present. So, either your inertia term will be comparable with buoyancy term or your viscous term will be comparable with buoyancy term, because to have the natural convection you should have the buoyancy term present. Okay. So, in two different cases now we will consider high Prandtl number fluids and low Prandtl number fluids. So, first we will consider high Prandtl number fluids. Okay. So, Prandtl number is much greater than 1. So, you can see your h by delta t to the power 4, Rayleigh number to the power minus 1 will be comparable with 1. So, that means viscous term will be comparable with buoyancy term, because Prandtl number is very high. So, the inertia term you can see you have 1 by Prandtl number. So, and Prandtl number is very high. So, that will be negligible compared to the viscous term, and for high Prandtl number fluids you can compare the viscous force with the buoyancy force. So, that we are doing. So, with this now you can find what is delta t. So, delta t will be order of h, Rayleigh number to the power minus 1 by 4. Okay. And we know that delta t by h, we have assumed that it is much greater than 1. From here you can see delta t by h will be order of R A h to the power minus 1 by 4. If delta t by h is much less than 1, then this Rayleigh number should be very high. Okay. because it is of the order of real number h to the power minus 1 by 4. So, it is minus is there. So, you can write the boundary layer theory for natural convection is valid for high Rayleigh number fluids. So, now you can find what is the scale of velocity v. So, we know v is order of alpha h by delta t square. So, delta t by h is r h to the power minus 1 by 4. So, from here you can write v will be alpha by h r h to the power half. Okay. So, this is the scale for velocity v for high Prandtl number fluids. Now, let us find what is the heat transfer coefficient. Okay. So, for heat transfer coefficient, so you know h is equal to minus k del t by del x, okay, at x equal to 0 divided by t w minus t infinity. Okay. So, as you know x is order of delta t and this delta t will be delta t. So, you can write h will be order of k by delta t. Okay. So, now Nusselt number, so it will be order of Nusselt number is h by k, right. So, based on height h. So, Nusselt number will be order of. So, you can see h is k by delta t, right, and delta t by h. So, it will be h by delta t. Okay, h by k is h by delta t. So, Nusselt number will be order of Rayleigh number to the power 1 by 4. So, you can see from the scale analysis we have found the scale for delta t, thermal boundary layer thickness, your velocity v and heat transfer coefficient and Nusselt number. So, you can see Nusselt number is order of R h to the power 1 by 4, right. So, later when we will do the analytical solution for the boundary layer equations for natural convection, you will find that Nusselt number will be order of Rayleigh number to the power 1 by 4. Now, let us see that for high Prandtl number fluids. Okay. So, obviously for a high Prandtl number fluids, delta t will be much smaller than delta, right, where delta t is your thermal boundary layer thickness and delta is your hydrodynamic boundary layer thickness. So, in this case you can see that this is your thermal boundary layer thickness. So, temperature will vary, okay. It will be high at the wall and gradually it will decrease, and in the quiescent medium obviously there will be temperature is to infinity and delta t will almost will become 0. Okay. So, this is the variation of temperature inside the thermal boundary layer, but as delta is much greater than delta t. So, the effect of velocity will be still there outside this thermal boundary layer, okay. And you can see in the outside there will be effect of this velocity and you will get maximum velocity, obviously it will be inside the thermal boundary layer. Okay. So, maximum velocity you will get inside the thermal boundary layer. So, inside the thermal boundary layer if you consider, so obviously your viscous force will be order of buoyancy force, that means friction force. Okay. So, because it is near to the solid wall, so the viscous effect will be there and viscous effect will be comparable to the buoyancy force. But in the unheated layer, okay, so you can see obviously your buoyancy will be absent, because there is no temperature difference outside this thermal boundary layer. So, your buoyancy force will be absent and your viscous force will be comparable with the inertia force. Okay. Now, you can see that outside the thermal boundary layer, okay, so you will have viscous force will be comparable with inertia force. Okay. So, you can see viscous force will be comparable with the, so this is your viscous, okay, and this is your inertia. So, from here you can see, so viscous term will be your nu into del 2 V by del x square will be comparable with the inertia term. So, that will be any term you can say. So, it will be, let us say, V into del V by del y. Okay. So, in this case now it will be nu V, but as it is outside the thermal boundary layer. So, x will be order of delta, which is your hydrodynamic boundary layer thickness. So, this will be delta. Okay. So, it will be delta square and it will be V square divided by y, obviously it will be order of h. So, it is order of h. So, from here you can see the velocity v will be order of nu h by delta square. Okay. And delta square you can write nu h by v, and you can write delta square as v we have already found, it will be alpha h by delta t square, right. So, if you put the value of v, so it will be nu h delta t square by alpha h. So, you can see delta square by delta t square. So, this h will get cancelled and nu by alpha is Prandtl number. Okay. So, you can see delta by delta t will be Prandtl number to the power half, which will be much greater than 1, right, because Prandtl number is greater than 1, and from here you can see that delta will be greater than delta t. Now, let us consider low Prandtl number fluids. Okay, that means Prandtl number will be much less than 1. Low Prandtl number fluids. So, in this particular case, now as Prandtl number is low, so inertia force will be dominant. Okay. So, you can neglect the viscous force. So, inertia force will be comparable with the buoyancy force, right. So, in this case inertia force will be comparable with buoyancy force. So, obviously it will be h by delta t RH to the power minus 1, Prandtl number to the power minus 1 will be order of 1. So, from here you can see delta t by h will be order of Rayleigh number h to the power minus 1 by 4, Prandtl number to the power minus 1 by 4. Okay. So, this is your delta t by h, and what will be the scale for velocity v? V will be alpha h by delta t square. So, v will be order of alpha by h R A h to the power half, Prandtl number to the power half. Okay. So, now you can see your Nusselt number. So, Nusselt number based on h will be order of h by delta t, we have already shown. So, Nusselt number h, from here you can see it will be order of R A h to the power 1 by 4, Prandtl number to the power 1 by 4. Okay. So, you can see we can conclude Rayleigh number into Prandtl number plays the same role for low Prandtl number fluids as Rayleigh number plays for high Prandtl number fluids, because for high Prandtl number fluids okay, we have shown that Nusselt number H will be order of Rayleigh number to the power 1 by 4. Okay, and this is for low Prandtl number fluids, and from here we will define another non-dimensional number that is known as Boussinesq number. Okay. So, this is product of Rayleigh number into Prandtl number. Okay. Rayleigh number into Prandtl number. So, you can write it as G beta delta T H cube by alpha square. So, Nusselt number you can see it will be order of Boussinesq number to the power 1 by 4. So, now in this case you see for low Prandtl number fluids. So, obviously your this is your thermal boundary layer thickness delta T. So, at the wall you will have high temperature difference, and at the edge of the boundary layer obviously the delta T will tends to 0. So, this is the delta T variation and the velocity. So, obviously as inside the thermal boundary layer buoyancy effect is there and there will be fluid motion, and as fluid motion will be there. So, you can see your velocity effect. So, this is the velocity. Okay. So, this is the velocity v. So, velocity effect will continue till the thermal boundary layer thickness. Okay. So, near to the thermal boundary layer thickness. So, obviously it effects will extend to the edge of thermal boundary layer. Okay. So, the effect of velocity or the fluid motion effect will extend to the edge of the thermal boundary layer. So, obviously it is due to the buoyancy effect inside the thermal boundary layer. So, you cannot say that your hydrodynamic boundary layer thickness will be much smaller than delta T for this low Prandtl number fluids. Okay. But you can see you have the maximum velocity near to the wall. So, this will be your maximum velocity, and if this thickness you can see this is delta V. Okay. So, viscous effect will be acting only near to the solid wall, and your viscous force will be balancing to the buoyancy force inside this layer delta V. But outside you can see viscous force will be less, and here inertia will be comparable with the buoyancy force. Okay. So, whatever we are introducing one thickness delta V, you have maximum velocity. So, inside this your viscous force will balance with the buoyancy force, but outside it your viscous force will be less, and you can compare inertia force with the buoyancy force. So, now you can see that let delta V is the thickness of a thin layer right near to the wall. Where viscous force will be comparable with the buoyancy force, because already we have shown that for low Prandtl number fluids inertia force will be comparable with the buoyancy force, and we have derived the thermal boundary layer thickness and the Nusselt number, but near to this wall now viscous force will be balancing with the buoyancy force, and from here you can see nu into del 2 V by del x square will be comparable with the G beta delta T. So, we know that x is order of, now in this case it is order of this delta V. Okay, delta V. So, you can write nu V divided by delta V square will be order of G beta into delta T. So, you can write delta V square will be order of nu v by g beta delta t. So, what is the order of v? It will be alpha h by delta t square, okay, alpha h by delta t square. So, now v will be order of alpha by h, Rayleigh number to the power half and Prandtl number to the power half. So, if you put this v here, so you will get delta v square will be nu into alpha, Rayleigh number to the power half, Prandtl number to the power half divided by h into g beta delta t. Okay. So, now we will rearrange it. So, if we rearrange, so you will get delta v square, it will be g beta delta t h cube into alpha nu, and you will get h square, and we have written h square, and you have R A h to the power half, Prandtl number to the power half. Okay. So, here you can see this is you can write as Rayleigh number. So, delta v by h square you can write as Prandtl number to the power half, Rayleigh number to the power half, and this term is Rayleigh number. Okay. So, you can write as Prandtl number to the power half divided by Rayleigh number to the power half. So, now we will define another non-dimensional number, that is known as Grashof number. Grashof number is the ratio of Rayleigh number to the Prandtl number. So, now we are defining another non-dimensional number, that is your Grashof number. So, Grashof number is your R A h by Prandtl number. So, from here, so you can see you can write delta v by h will be order of. So, it is your 1 by Grashof number, right. So, you can write Grashof number to the power minus 1 by 4. Okay. And from here now we have delta v by h, we have Grashof number to the power minus 1 by 4, and also we have delta t by h as Rayleigh number to the power minus 1 by 4, Prandtl number to the power minus 1 by 4. So, from here you can see delta v by delta t will be order of Prandtl number to the power half, and obviously it will be less than 1. So, delta v will be much less than delta t. So, you can see that it has to be noted that delta v is not same as the hydrodynamic boundary layer thickness delta. Okay. So, delta v is the thickness where your viscous force is comparable with the buoyancy force very near to the wall. Okay. And for low Prandtl number fluids, this delta v will be much less than your thermal boundary layer thickness delta t. So, in today's class we have introduced the natural convection. So, natural convection will occur in presence of some acceleration like gravity and density change, and density change may occur due to the temperature difference. So, in the beginning we have shown some applications of this natural convection, then we considered the simplest case flow over vertical wall, and we considered uniform wall temperature case starting from the Navier-Stokes equation, and using the boundary layer approximation we have written down the boundary layer equations, and from there we invoked the Boussinesq approximation. So, what is Boussinesq approximation? In Boussinesq approximation we assume that density to be constant in continuity equation as well as in the inertia terms of the momentum equations, but the change of density effect we take into account in the buoyancy term. From there we have used the scale analysis, and using scale analysis for two different cases low Prandtl number fluids and high Prandtl number fluids, we have shown the scale for thermal boundary layer thickness, velocity v, heat transfer coefficient and the Nusselt number. And for low Prandtl number fluids, we have also defined one thickness delta v, which is very near to the wall, where viscous force is comparable with the buoyancy force. Thank you.